good evening and welcome to Unacademy live YouTube classes. I'm Rashmi Ammar. I welcome you to this live session. I hope I'm audible to you. Okay. Let me start with introducing myself. I'm Rashmi Ammar. I'm teaching in Unacademy YouTube platform from past 4 classes. This is your 5th live class, is it not? So we started with alcohols, phenols and ethers chapter. Okay, I am a teacher since past 10 years. I'm teaching in various capacities in colleges as well as in different platforms. And Unacademy platform I'm teaching from this year, and it's been a great experience in teaching Unacademy special classes. And also students, you can subscribe to Unacademy Plus if you want comprehensive batch like PCM or PCMC or PCB batches. If you want all subjects which you're writing, okay, not just chemistry or not one subject, but all subject comprehensive batch, you can join Unacademy Plus classes. You have to subscribe to Unacademy Plus classes, where we'll have premium content in affordable prices. You can subscribe to 12-month, 6-month, or even for a period of 1 month. 12 month you're paying 12,375 rupees. 6 month you're paying 10,125 rupees, or for 1 month 2,250 rupees. Okay, well structured live classes, dedicated live doubt clearing sessions will be there. Not just quizzes, test series, daily practice problems, full length mock test, all will help you in self analysis. Okay, and what best of all the feature is, with a single subscription you have unlimited access. So any classes, anytime you can, as long as you have subscription, you can enter the class, you can learn. Okay, if you have doubt in the classes which you have already attended, recorded classes of same class will be available. So because you have subscription, you can log into those classes and you can relearn it. Okay, students, if you use my user code Rashmi 2020, in fact you need not pay this much, because you get 10% discount. You need not pay this much, you will get 10% discount. Okay, with this amount, you have 10% discount if you use my referral code Rashmi 2020. So you, your friends, neighbors, relatives, whoever are in PUC, spread the word. So everyone, let's get the benefit of it. Okay, let's continue. Avril, good evening and welcome to YouTube class. Okay, so we already started with oxidation. Okay, we know that all the oxidizing agents which are available. Okay, if you use strong oxidizing agent like potassium permanganate, okay, primary alcohol is converted into first aldehyde, followed by oxidation to give you carboxylic acid. So primary alcohol will be converted into carboxylic acid if we use strong oxidizing agent. So if they want the reaction to stop at aldehyde, then you have to use the CrO3 or PCC, pyridinium chlorochromate. PCC, short form for pyridinium chlorochromate is PCC. You use the CrO3, okay, chromic oxide, or PCC. The primary alcohol CH2OH is converted into CHO, aldehyde group. So the reaction stops there. So alcohol is converted into aldehyde. Okay, this is from primary alcohol. If we use secondary alcohol, see general formula for secondary alcohol is RCHOH R'. R' are 2 different alkyl groups. Okay, secondary alcohol on oxidation with the CrO3, you will get ketone. CHOH is converted into CO. You will get ketone. Okay, that is what happens to secondary alcohol. Primary alcohol will get aldehyde, RCHO with the CrO3. Secondary alcohol with the CrO3, we get RCOR, that is ketone. So secondary alcohol will give you ketone. See, for example, CH3OH. Okay, so this is secondary alcohol. In the presence of CrO3 as an oxidizing agent, what happens? CHOH becomes CO. So CHOH becomes CO, CH3. So this is acetone or propanone. Propanone. Prop, because 3 carbon atoms. 1, 2, 3 carbon atoms. So prop. Ane, because all between carbon single bond. And you have ketonic functional group, that is by ONE. Okay, and in ketonic functional group, when the ketone is the functional group, the smallest number possible for the ketonic carbon is 2. That is why when you don't write this, see, propane, 2-ONE you should have written. If 2 is not written, just a propanol you write. Understood that it is 2. Second carbon atom is ketonic carbon atom, ONE carbon atom. Okay, second carbon atom is ketonic carbon atom. Okay, so that is what you get. So when you use CrO3, secondary alcohol is converted to ketone. Now what happens to tertiary alcohol? Okay, yes. Okay, next is dehydrogenation. We will learn now here tertiary alcohol. What happens? Dehydrogenation. Okay, reaction is dehydrogenation. Now in dehydrogenation, the catalyst is quite different. Copper, heated copper we use at 573 Kelvin. Heated copper is heated to 573 Kelvin, and vapors of alcohol is passed over heated copper as a catalyst. Copper is the catalyst. Heated copper at 573 Kelvin, vapors of alcohol is passed over. So if primary alcohol is passed over heated copper at 573 Kelvin, primary alcoholic group, that CH2OH becomes a CHO. You get aldehyde. So primary alcohol becomes a aldehyde. Okay? Yes. So what happens? Dehydrogenation takes place. CHOH. See, look at this. 2 hydrogen less. CH2OH becomes CHO. So plus hydrogen is the product. Okay? So you are removing hydrogen. So it's called dehydrogenation. So primary alcohol, you are removing hydrogen. Okay? H2 group you are removing, you get aldehyde. Example, CH2, CH3, CH2OH. CH2OH becomes a CHO. So CH3, CH2OH becomes CH3CHO. That is ethanol. Ethanol becomes ethanol. Ethanol becomes ethanol. Okay? Plus hydrogen is the catalyst. Heated copper at 573 Kelvin. That is the primary alcohol. What happens to secondary alcohol? Same thing. Secondary alcohol, CHOH becomes a ketone. Okay, CHOH becomes ketone. You get a ketone as the product. Plus hydrogen. Again, dehydrogenation. Dehydrogenation takes place. Okay, you pass vapors of secondary alcohol over heated copper as a catalyst at 573 Kelvin. Hydrogen is removed. See H from here, carbon. So CH and OH bond is broken. So between carbon and oxygen, double bond appears. So removing hydrogen. Dehydrogenation takes place. See example. This is secondary alcohol. See CH3, CH. OH, CH3. Carbon to which OH is attached, in turn attached to other carbon atoms. Carbon to which OH is attached, in turn attached to other carbon atoms. So this is a secondary alcohol. Okay, so hydrogen is removed. Carbon hydrogen bond breaks, oxygen hydrogen bond breaks. So you get byproduct H2. So between carbon and oxygen, double bond comes. So you get ketone. Propanol. Propanol is the product. Okay, again same reaction condition. Copper is the catalyst at 573 Kelvin. Now, tertiary alcohol. What happens to tertiary alcohol? This is the example for tertiary alcohol. So, this is the carbon to which OH is attached. In turn, attached to 1, 2, 3 carbon atoms. So, this is a tertiary alcohol. Tertiary alcohol do not undergo dehydrogenation. In fact, they undergo dehydration. That means you get byproduct to water because you are going to remove water molecule. So, the carbon to which OH is attached, it will come out. Okay. Now, this is, let's say, call this as alpha carbon. So, all this becomes a beta carbon. Okay, one of the beta carbon loses its hydrogen. Between those two carbons, double bond says, okay, if let's say this carbon loses its hydrogen. So OH and H forms water. So dehydration takes place. Between these two carbons, see, double bond appears. Okay, double bond comes. So you get alkene. You get an alkene. So tertiary alcohol will give you alkene. So remember, primary alcohol will give you aldehyde. Secondary alcohol will give you ketone. And tertiary alcohol will give you an alkene. This is the product of oxidation. So, okay, here these two, if it is a copper with the 573 Kelvin, this is dehydrogenation, the tertiary dehydration. We remove water. Okay, between carbon, the carbon which has OH and the carbon which loses H, between them double bond. So, what is the name of this compound? 1, 2, 3. So, this is the active center. So, carbon containing double bond should have smallest number. So 1, 2, 3. Second carbon has a methyl group. So it is 2 methyl to 3 carbon. So prop, okay, 2 methyl, 3 carbon. So prop, okay, and 1 ene. It's not now ene, propane. Instead of ene, it is ene. And which carbon? First carbon. So you can write 3 methyl propene or 3 methyl prop 1 ene. So this is the result of reaction with the copper at 573 with the tertiary alcohol. Alkene is the product. Okay. Yes. Next reaction is reactions of phenol. See, here completes reactions of alcohols. Now next is reactions of phenols. And when we discuss reactions of phenol, we will be learning about electrophilic substitution reaction. Okay, because we have phenol, we have benzene ring. Benzene is an electron rich center. Okay, electron rich center. So since it is electron rich, it will act like a nucleophile. Okay, you cannot substitute nucleophile to a nucleophile. So it has to be an electrophile. Electrophilic substitution takes place because the opposites attract. Electron rich benzene ring attracts the electron deficient species. So electrophilic substitution reaction takes place. Hydrogen, see this carbon has OH. These 5 carbon atoms has hydrogen. So hydrogen atom will be replaced by electrophile. Now, since there are, with respect to this carbon number 1, okay, with respect to this carbon, these 2 are ortho positions, these 2 are meta positions, this is a para position. Now, where is the substitution taking place? Okay, now OH group, O oxygen atom, let me show you here. This is benzene ring. Okay, oxygen has 2 lone pair of electrons, and benzene being electron rich, it's also an electron withdrawing group. It is electron rich. Why? Because it has 3 pairs of pi electrons. 6 pi electrons are there, okay, which is present above and below on the plane of this molecule. Okay, this is electron rich, but it is also an electron withdrawing group. It withdraws lone pair of electron from oxygen and brings it to resonance. So when electrons are withdrawn, these electrons jump to this ortho carbon atom. So this goes to resonance like this. So you get resonance structure like this. So now the ortho carbon is electron rich. Double bond comes oxygen between oxygen and this carbon. Double bond comes H. Oxygen lost 1 electron to this carbon. So plus bond appears. Okay. So like this. Now this electron cannot be remain in one carbon atom. So it moves between carbon atoms, second and the third carbon atom. So this pi electron never next. See, if I write like this, I will get like this, right? Okay, this part is as it is, OH with a plus. So I have multiple bond like this. Never 2 pi bonds exist next to each other. That is why the pi electron from here moves to the next available carbon atom, this. So now ortho become ortho to para. See, from ortho was electron rich, now it is para. Again, para electron moves to between these 2 carbon atoms. So the pi electron moves to next carbon atom. Again, ortho position. So next resonance structure you get. Okay. So you have now here, now electron here, double bond, OH plus. Now electron will come back here. So the electron move back to oxygen. So you get the original molecule like this. Of course, with the shift in the double bond. See, look at the double bond position. Double bond position has been changed. Okay, so these structures are called as canonical structures. Okay, and canonical structures, or we call it as resonance of phenol. Okay, this is how phenol undergo resonance. Now during this resonance, okay, if you notice, ortho, para, and ortho positions are electron rich. So incoming group is an electrophile. So electrophile, OH directs electrophiles to ortho and para position, because when they undergo resonance, ortho and para positions are electron rich. An electrophile will go to the carbon which is electron rich, and compared to all these carbons, 5 carbons, ortho and para positions are electron rich, not meta. Okay, compared to meta, ortho and para are carrying negative charge, they are electron rich. So electrophile is directed to ortho and para positions. Okay, so this is called as electrophilic substitution reaction, and in that first reaction we are learning is nitration. I hope you understood this. First reaction is nitration. Okay, nitration. Now nitration is carried out under 2 conditions. That first is using dilute nitric acid. Okay, how do you carry out nitration? 2 reactions we are going to learn now. Nitration with dilute nitric acid and nitration with concentrated nitric acid. So nitration with the dilute HNO3, that is nitric acid, and with the concentrated HNO3, nitric acid. Now, if you are using dilute nitric acid, you get a mixture of products, orthonitrophenol and paranitrophenol. So, phenol undergo nitration with dilute nitric acid at 298 Kelvin, at very low temperature, 298 Kelvin, you get a mixture of products, orthonitrophenol and paranitrophenol. See, electron-rich group propositions are ortho and para. So, that is what you get, orthonitrophenol and paranitrophenol. Now, these compounds, separation is a question. Okay, how do you separate them? Using steam distillation. Steam distillation technique is used to separate them. Now why? Because these have the boiling point is slightly different. Okay, these are different boiling points. So steam distillation has to be used. Now between ortho and para is high boiling than ortho. Why? Because see, in the case of orthonitrophenols, intramolecular hydrogen bonding takes place. Okay, this is a OH group, and nitro group, NO2 group will be double bond O. Okay, like this. Now between the oxygen of nitro and hydrogen bonding takes place. This is called as intramolecular within the molecular hydrogen bonding. Okay, hydrogen bonding. Whereas in the case of para, between two molecules hydrogen bonding takes place. Okay, if this is one molecule and double bond O minus, O like this. Another molecule will be like this. Okay, let me write around this. OH, see like this. And you have NO2 here. See between the molecule, oxygen of nitrogen and H of OH group. See, OH, H and nitro groups O, between them hydrogen bonding. This is called as intermolecular hydrogen bonding. This is high, they are high boiling. So because of the difference in the nature of hydrogen bonding, ortho forms intramolecular hydrogen bonding, whereas para-nitrophenols form intermolecular hydrogen bonding. Paraphenols are high boiling compounds, whereas ortho are less boiling compounds or low boiling compounds. Okay, so they boil off first, leaving the para behind. So you can, by steam distillation, you can separate these two compounds, orthonitrophenol and paranitrophenol, separated by steam distillation because of the difference in their boiling point, because of the nature of hydrogen bonding. Orthonitrophenol forms intramolecular nitrogen bonding, whereas paranitrophenol forms intermolecular nitrogen bonding. So that is with the dilute nitric acid, you get two products. But if we use concentrated nitric acid, okay, when phenol is treated with the concentrated nitric acid, you get one compound called as 2,4,6 trinitrophenol, both ortho and para. Okay, both orthos and the para, all the three parts where electron rich parts of the benzene ring. All the three positions will be filled by nitro group. So OH group will direct both ortho as well as para group filled with NO2. It directs incoming electrophile NO2 to both ortho and para positions. So you get, with respect to this is carbon number 1, 2, 3, 4, 5, 6. So you get 2,4,6 trinitrophenol, and this is called as picric acid, which is an yellow crystalline solid. Which has a bitter taste. Okay, picric acid comes from the Greek word which means bitter, so it has a bitter taste. Okay, yellow crystalline solid, 2,4,6 trinitrophenol is picric acid. I hope you understood this. Okay, any doubt? Okay, that is with the nitric acid, nitration. Okay, depending upon what kind of a nitric acid you take. Dilute means you get a mixture of ortho and paranitrophenol. If you take concentrated nitric acid, you get only one product, picric acid. That is nitration. Second electrophilic substitution reaction is halogenation. Okay, now phenol is treated with the halogen. Now when I say halogenation, we are exclusively talking about bromination. And we are going to carry out bromination in two ways. One is bromine in inert solvents like CS2 or CHCl3, inert solvents like carbon disulfide or chloroform. These are called as inert solvents. Okay, or you are going to carry out reaction bromine in water, whereas water is an active solvent. Okay, product differs whether you are carrying out bromination in inert solvent or bromine in water, product varies. If you are carrying out bromination in inert solvents like CS2 at low temperature 273 Kelvin, you get a mixture of product. You get a ortho bromophenol and para bromophenol. Okay, ortho bromophenol and para bromophenol. Now if you discuss, do you get equimolar or equal amount of these two products? No, always para bromophenol is the major product. Why? Because of the symmetry. The two bulkier groups at opposite ends, so less repulsion, more stable than sitting next to each other. Here, because of the steric hindrance, okay, ortho substituted product is less stable, so they are minor products. So major products are para substituted products. So para bromophenol is major product and ortho bromophenol is minor product. So bromine in CS2, you get these two products. Whereas if you are carrying out bromine in water, okay, you get tri-substituted product, or 2, with respect to this 2, 4, 6. So 2,4,6 tribromophenol is the product, which is a white colored precipitate. So this can also be used for detection of phenol. Because if phenol is present, brown color of the bromine, reddish brown color of the bromine will be discharged. Okay, you get a white colored precipitate because substitution is taking place. So brown color discharge, because when the bond between Br is broken, okay, when they are getting substituted, the brown color gets discharged and you get a white colored precipitate. Okay, so it is called as 2, 4, tribromophenol. Now, why do they react separately? Why in CS2 they form two products? Why in water, bromination, water forms only one product? Why? Because in the presence of water, okay, in the presence of water, okay, phenol form phenoxide ion. This is phenoxide ion. O minus ion. Okay, phenoxide ion. And phenoxide ion is more electrophilic than phenol. Phenoxide ion is more electrophilic than phenol. Okay, because of this, bromination with the bromine water, okay, becomes easy, and you get tri-substituted product. Because the phenoxide ion will direct the bromine to ortho and para positions, you get tri-substituted product. But if the water is absent, in the absence of water, that is when the reaction is carried out in CS2, in the absence of water, in the presence of CS2 or CHCl3, okay, at 273 Kelvin, phenol is less reactive. Now you have only phenol, which is less reactive. I told you phenoxide is more reactive than phenol. Okay, so now phenol is less reactive. So you get ortho and para substituted product. Okay, not only that, okay, due to the presence of OH, okay, OH is very activating group. It's because of its activating nature. You don't even have to have any Lewis acid catalyst like FeCl3 or FeBr3 in the case of FeBr3 here, because bromination. You need not have any Lewis acid catalyst. In the absence of catalyst also, because of the activating nature of OH, ortho and para portions are activated, you will get these products. Okay, so in the case in the bromination of phenol, you need not have any Lewis acid catalyst. Why? Because OH is activating in nature. That is why ortho and para products are obtained. Now, why two products? Because phenol is less reactive than phenoxide ion. Whereas in water, phenoxide ion is present, which is more reactive. Okay, so you get tri-substituted product. Tri-substituted product. I hope you understood this. I hope you understood this. Yes? Any question? Any question? Okay, now let's go to next reaction, that is coal-based reaction. Very, very, very important, coal-based reaction. Okay, now what is coal-based reaction? What is coal-based reaction will be asked. So you have to write this. When phenol reacts with sodium hydroxide to form sodium phenoxide. This is called a sodium phenoxide. Okay, minus ion is phenoxide ion, so sodium phenoxide. Okay, so phenol reacts with sodium hydroxide, OH becomes so ONE. That is what is called a sodium phenoxide, which undergoes electrophilic substitution reaction with the carbon dioxide at 413 Kelvin and 6 to 7 atmosphere. Okay, this temperature is very important. 413 Kelvin and 6 to 7 atmosphere. Okay, this is the temperature, 413 Kelvin, and pressure is 6 to 7 atmosphere. Okay, sodium phenoxide undergo electrophilic substitution reaction with the carbon dioxide, followed by acidification. See, when this is the second step. With the carbon dioxide, this is the product formed. Okay, before this formed, so this is the product formed. You will get and COONA. COONA you get. Okay, which on treatment with the acid HCl, you get this compound, salicylic acid. So if I have to write this reaction is like this. Okay, phenol reacts with the first step, sodium hydroxide. You get sodium phenoxide, ON. Now sodium phenoxide reacts with CO2 at 413 Kelvin and 6 to 7 atmospheric pressure to give you sodium salt of salicylic acid, which on treatment with acid OH COONA, on treatment with acid on acid hydrolysis, you get salicylic acid OH COOH. Okay, plus of course NaCl, plus NaCl. So Na and Cl, H will substitute. Okay, you get salicylic acid. Salicylic acid is also called as, see, with respect to when you have OH and COH, okay, you know that COH is your functional group, OH becomes a substituent. So this substituent. So this has to be written in as a prefix. OH is written as a prefix. And with respect to this COH, this is the ortho position. So you can write orthohydroxy benzoic acid. Or with respect to this is carbon number 1, this is carbon number 2. Or 2-hydroxy benzoic acid. Or common name salicylic acid. So when you have COH and OH, COH is the functional group. This is carbon number 1. Okay, to which COH is attached. So with respect to this is carbon number 2. So OH becomes hydroxy. Substituted is, so prefix. Okay, so this compound is a benzoic acid. OH is a substituent, so it should be written as a prefix. So attach to second carbon atom. So 2-hydroxy benzoic acid or salicylic acid. 2-hydroxybenzoic acid or salicylic acid. Okay, now we have to notice here two things. One is, if the temperature is above 413 Kelvin, okay, if temperature has, I told you temperature has to be 413 Kelvin. If the above reaction takes place above 413 Kelvin, you do not get salicylic acid. In fact, OH will be on the para. You get para isomer is formed. Predominantly para isomer is formed. That is, this compound is formed. Okay, COOH and OH, like this. Para isomer is formed. So that is why the temperature has to be 413. Above 413, you will not get salicylic acid. That is one thing. Second group is, during if you notice, the sodium phenoxide will give you sodium salicylic acid or sodium salt of salicylic acid. Okay, COOH, that H is converted to Na. Why? Because not C, you don't have ONA. This is not ONA and COH. Okay, it is OHCONA it becomes, because it started with the ONA. ONA converted into OH, okay, and CONA is added, because COH, this group is more acidic than OH. COH group is more acidic. That is why that is contained sodium salt of carboxylic acid, CONA, which an acidification converted into COH. I hope you understood. Okay, so if you have to notice, if you have to understand this, simple as this. Carboxylic acid group, COH is carboxylic acid, is more acidic. Okay, so when you have OH and COH, CONA is the reaction you get. CONA is the group you get. Okay, sodium hydroxide converts COH into CONA, not OH. Okay, COH is attacked, converted into CONA. Okay, or else you can simply write like this. Okay, reaction of phenol with sodium hydroxide, giving you sodium phenoxide. Iron first reacts with carbon dioxide, then with acid hydrolysis, you get 2-hydroxybenzoic acid or salicylic acid. Salicylic acid. That is coal-based reaction. Any doubt? Any doubt? I hope you understood. This is very, very important. What is coal-based reaction will come. So what is salicylic acid? Okay, now its IUPAC name, 2-hydroxybenzoic acid, or what is salicylic acid? Okay, you should know. And how do you prepare salicylic acid by coal-based reaction? Okay, what is the reaction? All this is very, very, very important. Okay, next, so coal-based name reaction. Next reaction is Reamer-Tiemann reaction. Reamer-Tiemann reaction. Now what is Reamer-Tiemann reaction? Phenol reacting with the phenol. Again, we are learning reactions of phenol. So starting material is phenol. Phenol reacting with the chloroform and aqueous solution of sodium hydroxide. Okay, you get an intermediate compound. This is called as benzyl chloride. Benzyl chloride. Now, so when phenol is treated with CHCl3 and NaOH, OH is converted into ONA, and from chloroform CHCl2 is attached to the ortho position. So this is the intermediate you get, called as benzyl chloride. Benzyl chloride. Okay, which on treatment with sodium hydroxide? Okay, you treat with sodium hydroxide, CHCl2 is converted into CHO. Okay, CHCl2 is converted into CHO, which on treatment with the acid, ONA becomes a OH. You get now OH and CHO next to each other in 1,2 position. Okay, you get salicyl aldehyde. Now ic acid you remove from salicylic acid. Okay, salicylic acid, ic acid you remove, you write aldehyde. That's all. Salicyl aldehyde. You get salicyl aldehyde. So on the ortho positions, if they are present, OH and CHO, they are called as salicyl aldehyde. Again, okay, now when you have an aldehyde group, this becomes your primary function group. Okay, so you have aldehyde group as a benzaldehyde. This is benzaldehyde. 2-hydroxybenzaldehyde. 2-hydroxybenzaldehyde is the product. Now I will tell you how exactly the reaction takes place. Okay, sort of mechanism of the reaction. So this is how the reaction takes place. You have phenol. Okay, we have a minute. I will tell you. We have phenol, which reacts with sodium hydroxide to give you sodium phenoxide, like this, ONA plus water. Sodium phenoxide, ONA, okay, orthohydrogen with the chloroform. Let me write chloroform like this now. Okay, this H and Cl, chloroforms, Cl and H of ortho position. Okay, you will get this compound, the intermediate benzyl chloride. So what is remaining from chloroform? CHCl2. That will get added here plus HCl. Now intermediate benzyl chloride. Okay, let me write it like this so it will be easy to understand. Carbon has an H and 2Cl like this with the 2 molecules of NaOH. Okay, NaNCl, second NaNCl, and this okay, sorry, yeah, like this, 2 NaCl, you will get ONA. This carbon has an H. This Cl is removed. In this place, OH is substituted. Okay, 2 NaCl you get. 2 NaCl you get. Because 2 sodium. So 2 Cl, NaCl. In its place, OH. Now you have OH, OH. Okay. Now that compound, ONA, with the carbon has H, OH, OH. Okay. Water molecule. Remove water molecule like this. What do you have now? ONA. Now CHO you have. This is CHO plus water molecule. Which on acidification? This on acidification with HCl, ONA becomes OH and CHO. Salicylaldehyde. This is the product. Salicylaldehyde is the product. Okay. This is how the reaction takes place. Kind of a mechanism of the reaction. Okay, so I hope you understood. We will, if you want, I will start with trimer reaction from here only, so you'll understand more steadily. Okay, and we'll complete phenols reaction and we'll start with the ethers. Okay, I hope you understood. Any doubt, students? Any doubt? Any doubt? No doubt? Okay then. See you in the next class. Okay. Till then, stay safe and happy Christmas. Since the Christmas week, happy Christmas.